So until this point, we have been studying different kinds of flow fields, primarily a step strain, where you essentially apply a step jump in strain at certain time, or step stress, which we have been calling creep. All right. We also are kind of discussing various ramps also in various problems. But what I'm going to now concentrate on is a very important flow field, which is called oscillatory flow field. All right. What is done in oscillatory flow field? In oscillatory flow field, you subject sample to oscillatory strain. Typically, oscillatory strain that is applied to a system is gamma is equal to gamma 0 sine omega t. All right. Where essentially this is the gamma 0. So this particular amplitude is gamma 0, while one particular period essentially represents omega t going from 0 to 2 pi. All right. So what is the importance of application of oscillatory flow field? And what kind of benefit it gives us as far as rheology is concerned? We shall first try to understand these questions, and then we shall move further to analyze the oscillatory flow field. All right. Let me mention this, that the oscillatory flow fields are I would say, one of the most important flow fields as far as rheology in general and linear viscoelasticity in particular. And why is that? Let's kind of try to understand that now. All right. Let's say that we have some kind of a soft material. All right. And it's been kept between two plates. All right. So let's kind of increase these plates, and let's say and what are we going to do is that we are going to move this top plate with respect to the bottom plate. Bottom plate is stationary. All right. And let's say the material that we have kept between these two plates is a soft material, which also means that it's a complex fluid or a structured material. Let's assume for a moment that it has a network structure. What is meaning of network structure? Network structure simply means that if I look at some kind of a region over here, I'll find that, let me just assume that it's some kind of a polymeric network is present in over here. Let's assume that. All right. It can be a covalently bonded network, or it can be a physical bonded network. All right. Now, if I move the top plate to such an extent that this network now gets stretched. All right. So let's say in a limit of equilibrium, let's say these are the two junction points. Let me represent junction points by some other color. Okay. So let's say these are the two junction points. All right. And then as the material undergoes deformation in this particular direction, let's say with respect to this point, this junction point will get stretched like this. All right. Now, beyond a certain point, assuming that there is no slip at the wall, which we shall always assume, the deformation that this two junctions will undergo will be so high that this particular molecule will come out of this junction. If it's a physical junction, then it will certainly come out and the junction will break. It will essentially remain like this, while this junction will remain the way it is. All right. So we have two possibilities. One possibility is junction getting extensively stretched is first possibility, and junction getting broken is the second possibility. All right. Now we know that if this particular polymer strand follows a spring-like behavior, we have been seeing spring and dashpot, then we know that spring will behave something like this, where stress will be proportional to strain. All right. So when the deformation or strain induced in the material is not significantly large, so that deformation induced in this particular chain is not much, we can very comfortably assume that stress is proportional to strain, which means that there is a linear relationship between them. However, as this particular chain gets stretched significantly, this particular spring may not behave any more like a linear spring. All right. And it may behave something like sigma going to the power something like gamma to the power n. All right. Which means that now this has become a nonlinear spring because of the stretching that it has been subjected to. And for this particular third case, you can see that there is a structure broken over here. So we will not be able to get the behavior of the material whose structure is intact anyway. All right. So if we are now interested in understanding the rheological behavior of the material, all right, we must apply small enough strain to the material so that its structure behaves in a much more regular way, which means that stress is proportional to strain, or stress is proportional to strain rate if it's a viscous dominated material. All right. We are not even interested in a state to begin with. All right. Now, how material undergoes or how material responds when the strain or deformation field becomes excessively large is also a very interesting topic. But to begin with, we are interested in characterizing the intrinsic structure of the material. All right. And that intrinsic structure of the material is essentially can be represented when the applied deformation field is such that the response is linear. All right. And such kind of applied deformation field can be, linear deformation field can be very easily applied in a sinusoidal flow field. You can imagine that when we apply step strain, what we'll have to do is that we need to keep this step strain that is applied over here in a limit which is below the limit where we call it linear limit. What is linear limit? Where stress is proportional to strain or stress is proportional to strain rate if it's a viscous dominated material. All right. So in step strain, we shall have to kind of apply this field, or when you apply step stress to the material. So this is strain and this is stress. Let's say step strain or stress is applied at certain time t. Then when you apply step stress to the material, now how much strain should get induced in the material is no longer in your hand. It really depends on the magnitude of stress that you have applied and the material response. All right. So if the magnitude of strain that gets induced in the material is small enough so that either linear stress proportional to strain relationship or stress proportional to strain rate relationship is obeyed, only up to that point the material response will remain linear. All right. Beauty of applying oscillatory strain field is that you can very well control the magnitude of strain that you have subjected to which you have subjected the material to. All right. So there are two kind of aspects which are input as far as this flow field is concerned. One is of course magnitude of strain, and second is of course the frequency of oscillation. All right. Now the frequency of oscillation is this omega. All right. So magnitude of strain and frequency of oscillation are essentially the two inputs. However, we shall see that when the behavior is in the linear domain, when stress is proportional to strain or stress is proportional to strain rate, the characteristic features of the material, all I should say the response functions of the material or properties of the material in rheological terms become independent of magnitude of strain. All right. That does not happen when the nonlinear response essentially kind of gets acted upon the material. or the deformation field is such that the material response is nonlinear, under those conditions, the response functions or the rheological properties of the material also depend on the magnitude of strain. But here is a domain which we call a linear domain, wherein properties of the material, rheological properties of the material are independent of applied strain. All right. And there comes the kind of importance of application of oscillatory flow field. All right. So we are going to discuss oscillatory flow field for a few more video lectures. So what I'm going to do now is that I'm just going to kind of give you introduction to a new set of response functions which originate because of application of oscillatory flow field. All right. So for that, what I'm going to do is that I'm going to start with two extreme states. All right. One state, of course, is elastic solid. Okay. So as a matter of fact, at the present observation time scale of a human being, we can certainly distinguish between two extremes. One is elastic solid. All right. Other one is viscous liquid, which simply means that relaxation time of elastic solid essentially tends to infinity, while relaxation time of this viscous liquid is essentially tends to 0. All right. We can also say that relaxation time compared to observation time scale. Okay. So I'll say simply this T observer and this T observer. Okay, which simply means that the relaxation time is extremely small compared to the observation time scale, and we have a viscous liquid. Relaxation time is very, very high compared to the observation time scale. So therefore, we have a elastic solid. All right. And what is the response of viscous liquid vis-a-vis elastic solid? When you have elastic solid, we know that stress is proportional to strain in a linear fashion. In case of viscous liquid, we have stress is proportional to rate of strain. All right. So this essentially is our, these are the two extremes that we have. All right. Now, what we are going to do is that we are going to subject both these extremes, the elastic solid as well as viscous liquid, to oscillatory strain field. All right. And let's see what happens. Okay. So first we shall study these two cases, and then we shall study something intermediate, which of course is viscoelastic. All right. So first we are going to talk about perfectly elastic, then we'll talk about perfectly viscous, and then eventually we'll talk about something which is viscoelastic in nature. All right. So let us move on. So as we said that we subject material to oscillatory flow field. So this first response, the first sinusoidal waveform that you're seeing is actually the strain that we apply to material. All right. And you can very clearly see that this strain, if this is the gamma 0, of course, minus gamma 0 here and plus gamma 0 here, then this sine wave that you can see over here is nothing but represented over here, which is gamma equal to gamma 0 sine omega t. All right. And I can also represent it in terms of a complex number, which is gamma is equal to minus gamma 0 e to the power I omega t. Now, please keep in mind that we already know that e to the power I theta is nothing but cos theta plus I sine theta. All right. So if you're talking about real part of I e to the power I omega t, then you will see that we indeed get sine omega t, minus sine omega t. So therefore this minus sign is over here, and this whole thing, real part of which will essentially give us this. All right. There are benefits of representing this in a complex form, which we shall kind of appreciate much better in the next class, but we shall kind of keep this nomenclature at this particular moment so that you'll be able to appreciate this nomenclature in both ways, just by mention of gamma equal to gamma 0 sine omega t, as well as in the complex number format. But keep in mind that we are talking about only the real part of this complex number at this present moment. All right. So if this is strain applied to the material, corresponding strain rate is nothing but derivative of it. So it is nothing but gamma 0 omega cos omega t. All right. If you see derivative of this becomes this. All right. So we have gamma now and we have gamma dot. All right. Both are not independent of each other. Both are essentially both represent one and the same thing. One is simply derivative of the other. All right. So when you apply gamma equal to gamma 0 sine omega t, at the same time, you're also applying gamma dot equal to gamma 0 omega cos omega t in the material. All right. So it's as simple as that. We have also represented it in the complex form, which is gamma 0 omega I e to the power I omega t. All right. So this is the flow field material is subjected to. All right. And now let us ask a very simple question to ourselves. And that question is, if a material is purely elastic solid, which means that sigma 12, the shear component of the stress tensor for elastic solid is simply proportional to modulus into the shear strain. And if that's the case, then if it's elastic solid, then it's very straightforward. This particular part will become essentially over here. So which simply means that stress induced in the material is proportional to strain. So therefore sigma 12 will be gamma 0 sine omega t, which is in complex form is simply this. All right. So when material is perfectly elastic in nature, the corresponding stress will also have a sinusoidal behavior, will also show sinusoidal behavior, whose crest as well as trough will precisely match the times associated with the strain input. So the corresponding trough and crest of the stress output will precisely match with that of the strain input. All right. Why? Because stress is proportional to strain and strain is sine omega t, gamma 0 sine omega t. All right. So therefore, stress also has to be sigma 0 sine omega t. Magnitude will be different, obviously, because units are also different. All right. So you have strain in one case, stress in one case, but if strain is gamma 0 sine omega t, then stress will also be sigma 0 sine omega t. All right. On the other hand, if you have a viscous liquid, then what will happen? Then stress is proportional to now gamma dot. All right. Which means that stress will show gamma 0 cos omega t behavior. All right. What does that mean? This means that the stress will follow the identical waveform as that of associated with the gamma dot, but with magnitude of sigma 0. All right. And we know that the very fact that gamma and gamma dot are essentially related in such a fashion that gamma dot is a derivative of gamma, which means that there is always a 90 degrees phase angle between the two, which means that crest of one is 90 degrees separated with respect to crest of the other. So crest of shear rate is, it lags behind by 90 degrees with respect to crest of the strain. Is that all right? So, which also means that when there is such a lag of 90 degrees, or pi by 2 in rheology, we call it out of phase. Okay, so we shall use a term in phase for elastic solid. So elastic solid are, for elastic solids, stress is in phase with strain. All right. For viscous liquid, stress is in phase with strain rate, which also means that for elastic solid, stress is out of phase with strain rate, and for viscous liquids, stress is out of phase with strain. All right. So this is the nomenclature that we shall use. All right. So I hope you have understood this particular aspect, that for elastic solid, the stress will also have absolutely identical stress waveform output, which is sinusoidal in nature, which is perfectly in phase with the strain, because stress is proportional to strain as far as elastic solids are concerned. For viscous liquids also, the stress waveform will be sinusoidal in nature, but it will be in perfect it will be in phase with strain rate, and it will be out of phase with strain. All right, so you should keep this aspect in mind. All right, now what happens in case of viscoelastic material? All right, and now we have been seeing this uh, in our spring dashpot models, as well as various other very general linear viscoelastic expression that we have obtained, that the behavior of viscoelastic material is in between the perfectly elastic behavior and perfectly viscous behavior. All right, and this behavior very strongly depends on the observation time scale. What is observation time scale over here? Observation time scale over here is associated with the frequency with which you are applying this particular sinusoidal strain. All right, so see the beauty of this experiment. All right, when you apply step strain or when you apply step stress, the observation time scale is the simply time elapsed since you have applied the step strain or step stress. All right. In case of oscillatory flow field, the observation time scale is associated with the frequency of application of that particular step strain or step stress. And you can then write down the observation time scale therefore as 2 pi by omega, then becomes your observation time scale. All right. So if your omega is extremely large, which means the frequency is very large, then the observation time scale becomes very small. If your frequency is very slow, very small, then the observation time scale becomes very slow. Before moving further, let me just make one small correction, that there is no I in this particular expression. All right. So keep that in mind. Okay. So now we shall discuss the viscoelastic response in greater details. Again, let me take a small recap here, that strain is a sine cycle while strain rate is a cos cycle. All right. So this is strain and this is strain rate. All right. On the other hand, this particular one is stress. All right. And the trough of strain is over here, while trough of strain rate is over here. All right. So therefore, of course, this stress cycle would be sinusoidal, and later when we'll talk about nonlinear oscillations, we shall discuss that when we are in the linear domain, the strain response is always sinusoidal in nature. Sinusoidal means it's a perfect sine wave. It may get shifted depending upon the extent of viscoelasticity of a material. All right. So it's a perfect sinusoidal type of response. The trough of this is has to be in between that associated with strain rate and that associated with the strain. All right. If this trough is precisely at the position where a trough of strain rate comes, then obviously response is viscous, because then the stress becomes proportional to strain rate. If this trough is at the point or at the same angle as where the trough of strain comes, then response would be perfectly elastic in nature, because for elastic materials, stress is proportional to strain. All right. In general, for a viscoelastic material, the trough of strain, trough of stress is in between that associated with strain rate as well as that of strain. All right. So we represent it to be shifted precisely lagging behind that of strain by angle delta. All right. And that particular expression is shown over here. All right. That sigma 1 2 equal to sigma 0 sine omega t plus delta. All right. When this delta is equal to 0, you have perfectly elastic response, while this delta is equal to pi by 2, you have perfectly viscous response. All right. And in complex form, we can represent it in this particular fashion where we are only considering the real part of this particular complex number. All right. Now, obviously, the stress response for viscoelastic material is in between the cos wave, the cos wave associated with gamma dot and sine wave associated with the strain. All right. So, in order to see that how much percentage of this particular stress response is in phase with strain and how much part of it is in phase with strain rate, we essentially open up this sigma 0 sine omega t plus delta, and we know that sine A plus B is nothing but sine A cos B plus cos A sine B. So we essentially write down this particular part as sigma 0 cos delta sine omega t and sigma 0 sine delta cos omega t. All right. Now you can appreciate that sine omega t is that part of the stress response which is in phase with strain, while sigma 0 sine delta is that part of the stress response which is in phase with strain rate. All right. So this is the magnitude of stress which is in phase with strain, while this is the magnitude of stress which is in phase with strain rate. All right. So, but still this is stress. So this is one part of the magnitude of stress. This is another part of the magnitude of stress. And if we actually represent a modulus by stress divided by magnitude of strain. All right. But now we have two different types of stresses. One part of the stress is that stress which is in phase with strain. Other part is that stress which is out of phase with strain. All right. So we can simply represent this particular aspect now as sigma 1 2 prime sine omega t plus sigma 1 2 double prime cos omega t. All right. So what we have done is that magnitude of stress which is in phase with strain, we are calling it sigma 1 2 prime, while magnitude of stress which is out of phase with strain, which we are calling it to be sigma 1 2 double prime. Okay. So this is the magnitude in phase with strain and this is out of phase with strain. All right. Now this is G. Now modulus has a very uniform definition that it is stress divided by gamma 0. All right. So based on this in phase part and out of phase part, now we define G prime to be modulus of stress, a modulus associated with that stress which is in phase with strain. So we call it G12 prime divided by sigma 0, while we'll now represent G double prime as sigma 1 2 double prime divided by gamma 0. All right. But what is sigma 1 2 prime? Sigma 1 2 prime is nothing but sigma 0 cos delta, while sigma 1 to double prime is sigma 0 sine delta, as it's very clearly shown over here. So therefore our G prime becomes sigma 0 by gamma 0 cos delta, while our G double prime becomes sigma 0 by gamma 0 sine delta. All right. This particular G prime is known as elastic modulus. So G prime, which is associated with that part of stress which is in phase with strain. So therefore it represents elasticity. This is known as elastic modulus, while G double prime is equal to sigma 1 to double prime by gamma 0. This is the stress. Sigma 1 to double prime is that part of the stress which is in phase with gamma dot, all right? And stress proportional to gamma dot is the viscous behavior. So this particular modulus is known as viscous modulus. All right. And this sigma 1 2 is nothing but sigma 0 cos delta, and sigma 1 2 prime is sigma 0 cos delta, and sigma 1 2 double prime is sigma 0 sin delta. All right. This is how elastic modulus and viscous modulus have been defined. All right. Elastic modulus and viscous modulus are also known as storage modulus. Okay, so G prime is also known as storage modulus. Why it is known as storage modulus? Because it represents elasticity associated with the material. Elasticity means energy gets stored in the material. All right. On the other hand, G double prime suggests loss because it represents the viscous nature of the material. So it represents loss of energy during a single cycle of oscillation. So it's known as loss modulus. So storage modulus is synonym to elastic modulus, and viscous modulus is synonym to loss modulus. All right. You should keep this particular aspect in mind. All right. So this definition of G prime and G double prime we simply obtained by resolving stress into in phase strain component and out of phase strain component. All right. There is another way of doing it. And that another way of doing it is now we have this complex number form or complex representation form of stress. All right. So what I'm going to do now is that we shall define, or the stress has been defined in a complex form as stress in a complex form equal to modulus in a complex form multiplied by strain in a complex form. All right. We already know that strain in a complex form represented like this. All right. While the stress in the complex form also we show in the previous slide is represented like this. All right. So now if we represent the complex modulus as G prime I G double prime, keep in mind that just a while back we defined what is G prime and what is G double prime. Now this is another alternate kind of but equivalent definition of G star, which is complex modulus. And what we are saying is that complex modulus is that modulus whose real part is elastic modulus, while its imaginary part is viscous modulus. All right. So this is a new definition where we define complex modulus in this particular fashion. All right. And now what we essentially do is that we say that stress is complex modulus times strain. All right. Please note that when oscillatory strain is being applied, even stress is in complex form. Obviously, the strain also is in a complex form. So we have this modulus also in a complex form, whose representation is G prime plus IG double prime. All right. So what we'll now simply do is that we'll simply incorporate what is gamma. Gamma is nothing but minus gamma 0 I e raised to I omega t. While stress, we just represented it in the previous slide, it is minus sigma 0 I e to the power I in bracket omega t plus delta. All right. Now, if we solve this particular equation, we'll get expression for G star. And as you can very clearly see, that expression for G star is as follows. So this negative on the both side become plus. This sigma 0 comes here as divided by gamma 0. So we can remove this part also. And we have this e to the power I omega t over here and e to the power I omega t over here. All right. So this I also goes, and what we essentially get is G star is equal to sigma 0 by gamma 0 I delta. All right. Now we know that e to the power I delta is nothing but, so we have G star is equal to G prime plus I G double prime is equal to sigma 0 by gamma 0. E to the power I delta is nothing but cos delta plus I sin delta, all right, which means that this simply gives us G prime to be equal to sigma 0 by gamma 0 cos delta and G double prime to be equal to sigma 0 by gamma 0 sin delta. And you can see that through this very simple complex analysis also, we get identical expressions for G prime in G double prime. All right. Now, significant part of this particular course, we shall be discussing physical meaning of G prime and G double prime and how to understand material response on one hand and material microstructure on the other hand by analyzing G prime and G double prime and its dependence on frequency. All right. There is another important parameter which I mentioned in the previous slide, but just kind of confirm that this G prime and G double prime shown on this slide is identical to what is written over here. All right. And the next important parameter that we must define is called tan delta. All right. And tan delta is nothing but equal to, it's very clearly from this expression as well as from this expression, that tan delta is equal to G double prime by G prime. All right. We shall continue discussing G prime and G double prime, its dependence on frequency and various other facets associated with this complex notation of modulus, which we call complex modulus, in next videos. Thank you.